Okay, second half of section 4.5, rank plus nullity. So let me just go over some definitions. Col A is the space spanned by the columns of a matrix A. Row A is the space spanned by the rows. And null A is the set of solutions to AX equals 0. We have already talked about finding a basis for null A and col A. So this was section 4.3. And this was section 4.3, had a little box. It says how to find a basis for null A and row A. So for null A, just solve AX equals 0. And for col A, reduce A to echelon form. Look at the pivot columns in B. And don't take those, take the corresponding columns from A. Now, what's new is finding a basis for row A. And so we've got A that's reduced to an echelon form B. So B is an echelon form. Just take the non-zero rows of B. So stay in the B matrix, take the non-zero rows of B. Elementary row operations will not change the row space of a matrix, but they will change the linear dependence relations. So you need to take the non-zero rows from B, not from A. Okay, so we'll do an example of that very soon. And then the rank plus nullity theorem I alluded to last time. Rank A is defined as the dimension of col A. The nullity of A is defined as the dimension of null A. And the theorem, the big theorem we looked at last time, number 2, rank plus nullity is n. The number of leading variables, which is the rank, in AX equals 0, plus the number of free variables is equal to the number of variables. And then the second part of it, which is part 1, is that the rank of A is equal to the rank of A transpose. Now what this says, the rank of A is the dimension of col A, and the rank of A transpose, well, the columns of A are the rows of A transpose, right? So this tells us that the dimension of col A is the same as the dimension of row A, even though they live in different spaces. So I'm not going to prove it because I don't think much is going to come from the proof. It's a short proof, but the dimension of col A is equal to the dimension of row A. All right. So suppose we have, so we're going to look at the theorem first, and then we'll do an example of finding a basis for row A, col A, and null A. So suppose A is 5 by 8, and it's got rank 5. So think of A as a map from R8 to R5. And the rank of A is 5, meaning the dimension of col A is 5. So the nullity of A, the nullity of A is 3, and that's because the rank, which is 5, plus the nullity, which I'll call x, has to be 8, which is the number of variables in AX equals 0. So what number would work? 3. Dimension row A. Dimension row A is the same as dimension col A, which is the rank. So that's 5. The rank of A transpose is the rank of A, which is 5. Okay, and now here's an interesting question. Is col A all of R5? So one thing you need to know is that the only n-dimensional subspace of Rn is Rn itself. So remember, A maps R8 to R5. Col A is a 5-dimensional subspace. It's 5-dimensional because we're given that. The rank is 5. 5-dimensional subspace of R5. The only 5-dimensional subspace of R5 is R5. So the answer is yes. Col A is all of R5. Is AX equal B consistent for all B? That's yes, because of the fact that col A is all of R5. So from section 4.2, reminding you of this fact, AX equal B is consistent for all B if and only if col A is all of Rm. Well, in this case, Rm is R5. We'll do more of these in a minute. Okay, so now I take a matrix A and it's row equivalent to a matrix B. So I have A and B and the row equivalent. Find a basis for row A. We want the so I'm using the cheat sheet from the first page that we want the non-zero rows of B. Okay, that's easy. There's two of them. And I'm going to put these vectors, since this is a row space, I'm going to put the vectors in row format, which is parentheses with commas in between. 1, 0, -3, -6. That's one vector. And the other one is 0, 1, 0, 0. Okay. Find a basis for col A. So the first two columns of B are the pivot columns. So we want to take the first two columns of A. So we want -1, 2, and 1. And we want 2, -5, and -3. Find a basis for null A. We can just solve Bx equals 0. Since B is row equivalent to A, B is already in reduced echelon form. So what I did is just augmented B with the 0 vector, and I don't have to do any reductions. There's 4 variables. I start at the bottom. X4, this is the only one where you actually have to do work. X4 is free, so we'll call it T. X3 is free, we'll call it S. X2, that second line reads X2 is 0, and X1 is 3S plus 6T. So a basis for null A is, I want an S vector and a T vector. I'll do the S's first. 3, 0, 1, 0. My T vector is 6, 0, 0, 1. And notice rank plus nullity is 4. The number of columns in A is 4. The rank is the dimension of col A. And the nullity is the dimension of null A. So 2 plus 2 is 4. Okay, so here are some fun problems. You don't have to do any computation. They're just thought problems. So I'm starting off by doing a problem that I've already answered, and it's important for the rest of these problems. If the solution of a non-homogeneous system, AX equals B, has, for example, 2 free variables, how many free variables does AX equals 0 have? And the answer is it's the same as the number of free variables as AX equal B. So if this has 2, then this is going to have 2. And the reason why is because free variables come from being either leading or non-leading. So if you're leading or non-leading, that's determined by pivot columns in A, which has nothing to do with what you augmented with. So for example, if I augment A with B and reduce, or if I augment A with 0 and reduce, the first part, the part before the answer column, will be identical. So any pivots over here will be pivots over here. So use that fact to answer the next one. Suppose AX equals 0 has 1 free variable. Can AX equal B have a unique solution for some value of B? Can it have a unique solution? The answer is no, since AX equal B has 1 free variable. So if it has 1 free variable, that means infinitely many solutions. It can't have a unique solution. The only way it could have a unique solution is if there's no free variables. The only way that could happen is if AX equals 0 had no free variables. Okay, what's the largest possible rank of A if A is 4 by 3? Well, rank is the dimension of the column space. If there's only 3 columns, the largest the rank could be is 3. What if A is 3 by 4? Well, you might say the largest the rank could be is 4 because there's 4 columns. But remember, dimension row A is the same as the dimension of col A. Col A. So if there's only 3 rows, the maximum the row space could be is 3, the dimension of the row space. So the maximum the dimension of the column space could be is 3. So this is also 3. In general, if you have an M by N matrix, the largest rank is the smaller of the two numbers M and N. So this is going to be the minimum of M and N. All right. Next one, suppose A is 9 by 12. What's the smallest nullity that A could have? All right. Well, the maximum rank would be 9, because 9 is the smaller of 9 and 12. If the maximum rank is 9, then the minimum nullity, is 3, because rank plus nullity has to be 12. Rank plus nullity has to be 12. The nullity will be the smallest when the rank is the largest, but the largest the rank can be is 9. Okay. A is 5 by 6, and A has 4 pivot columns. So we're told that the rank, this means e.g., not e.g., but i.e., rank A is 4. What is the nullity of A? Well, the rank plus nullity has to be 6. So the nullity of A is 2. Is col A R4? So this requires a little bit of thought. We have to think about where A is going from and to. A is 5 by 6, so A maps R6 to R5. Col A has dimension 4, so is a 4-dimensional subspace of, where does col A live? It lives over here in the codomain. Col A is a 4-dimensional subspace of R5. R4 is not even a subset of R5. So the best you can say is col A is a 4-dimensional subspace of R5. But no, it's not R4. So the answer is no. Is null A R2? Well, again, we need to think about this. Null A has dimension 2. Null A is a 2-dimensional subspace of, where does it live? Null A lives in the domain, so 2-dimensional subspace of R6. So the answer is no. R2 is not a 2-dimensional subspace of R6. Okay, when can you answer yes? You might be confused at this point. So the answers here are no and no. Let me show you when you can answer yes. Suppose A is 7 by 11 and A has 7 pivot columns. So the rank of A is 7. And A maps R11 to R7. So col A, we're told, has dimension 7. So is a 7-dimensional subspace of, col A lives over here, R7. The only 7-dimensional subspace of R7 is R7 itself. So the answer is yes. So there's when you can answer yes. If you have a n-dimensional subspace of Rn, then that space is Rn. If you have a 2-dimensional subspace of R3, then it's not R2. So these were no, and these will be, well, I don't know about this one. If it's yes or no, we'll find out. Is null A R4? So first of all, what is the dimension of null A? If the rank is 7, then 7 plus the nullity is 11. 7, 8, 9, 10, 11. So the dimension of null A is 4. So null A is a 4-dimensional subspace of, where does null A live? It lives over here in R11. So no, a 4-dimensional subspace of R11 is not R4. So here's a yes and there's a no. So that's a good example for you to keep in mind in terms of clearing up your confusion. All right, invertible matrix theorem. I'm not going to spend any time on this. We're just adding four more things. And I just want to point out here, the first two new statements are statements about vector spaces. If A is an invertible n by n matrix, then call A is all of Rn, and null A is the 0 vector space. So these are vector space statements. And these two statements are the corresponding dimension statements. So if call A is Rn, then the rank of A is n. If null A is the 0 vector space, then the nullity is 0. So these go two peas in a pod. O and P go with Q and R. I want to finish up with fascinating geometry illustration, which we're going to come back to in chapter 6. So we won't really spend much time on it now, but I just want to mention it now. Suppose A is an M by N matrix. There are 6 vectors. I gave the answer away. There are actually 4 vector spaces of interest, but we're going to start with 6. You've got row A, call A, null A transpose, row A transpose, and call A transpose. However, it's only 4 distinct spaces because row A is the same as call A transpose, so those guys are the same. Call A is the same as row A transpose, so those guys are the same. So that leaves us with 4 fundamental matrix spaces, and it's important to know where these guys live. A maps Rn to Rm. So A transpose maps Rm to Rn. Who lives in Rn? So here's A going from Rn to Rm. Null A lives over here. Let's do the low-hanging fruit first. Null A lives over here, and call A lives over here. A transpose goes from Rm to Rn, so null A transpose lives over here. And what's left in our fundamental, who haven't we taken care of up in this list? We haven't taken care of row A. Where does he live? Well, the rows for an M by N matrix have N entries. So like a 2 by 3 matrix, the rows live in R3. So row A lives here. Did I say that right? A 2 by 3 matrix, 1, 2, 3, 4, 5, 6. And I said the rows live in R3. That's right. The columns live in R2 and the rows live in R3. Okay. So this next example, I've taken a matrix and I've reduced it, and then I've taken its transpose and reduced it. I want to find a base. I'm going to look at these 4 vector spaces and show you how they live. So A is 2 by 3. So A maps R3 to R2. So null A and row A live in R3. They live in R3. And then call A and null A transpose, these guys live in R2. All right, let's find a basis for null A. So A is up here. If I, in my mind, I'm going to augment A with 0. So there are 3 variables. X3 would be free, X2 would be free, and X1 would be X3. So 1, 0, 1, and 0, 1, 0. The space spanned by 2 vectors in R3 that are not multiples of one another is a plane. So a picture of null A is this plane here. Now, a basis for row A, I want the non-zero rows of the reduced matrix. So I'm going to write this as a column vector, 1, 0, -1. So that's spanned by 1 vector, so that's a line. So I've got a plane, null A is a plane, row A is a line, but it's not just any plane and any line. Look at how they meet. When we start talking about orthogonality or being perpendicular, these 2 vector spaces are what we call orthogonal. If you take any vector in this space and dot it with any vector in this space, the dot product will be 0. And we'll see that in chapter 6, but I just want to preview it now. Likewise, call A and null A transpose, they're both lines in R2, but they're special lines. They meet orthogonally. So a basis for call A, we want so A has 1, so the reduced A has 1 pivot column, so I want to use that 1 column from A, so 1, 2. And then a basis for null A transpose, if you look up here at A transpose that I've reduced, we can see that X2 is free and X1 is -2t. So this would be -2, 1. And again, if I dot this vector with that vector, I see that I get 0. So they're situated in a very special way. Ooh. All right, and that, did I give you any practice problems? Yeah, you got a really easy problem where you just get to play with numbers, and then some fun true-false problems. And that's the end of, this was a huge section.